section 5.3, we learn about the definite integral and the fundamental theorem of calculus. And so that's going to involve area under the curve, the concept of a Riemann sum, and applications of definite integrals. To start with, you need to complete this group activity. The GeoGebra file is on the website, so you can open that up and play with the app there. But the idea is that you're going to be given this function here. And this function is f of x is equal to 5 minus 1/4 of x squared. And here at the top, you're going to have this big N, and this is going to represent the number of rectangles that are drawn. And right now it's set at 2, and you can see the 2 rectangles down here. And this B controls whether or not the rectangles are drawn on the right or the left side. Now, what does it mean to be a right rectangle versus a left rectangle? Well, since we have only 2 rectangles, we can see that the interval that we're talking about here, which is 1 to 3, is split up into 2 equal parts. So one part goes from 1 to 2, and the second part goes from 2 to 3. When you want a right rectangle, quote unquote, then what you do is you start on the right side of the partition. So this first subinterval is from 1 to 2. You start on the right side and you go up until you reach the function. And then at that point, that is the height of the rectangle. And then you just go ahead and draw in the rest of the rectangle. And for the second subinterval, from 2 to 3, you go ahead and go up from the right endpoint of the subinterval. In this case was a 3, so you go up the 3 until you hit the function curve. And then you go over there, and that creates your second rectangle. If n is larger, you just do this more times. But that's the difference between a left rectangle and a right rectangle. It indicates the point where you go up until you reach the function. Now, it doesn't have to be left or right. It could be a midpoint. It could be a third point. It could be any point sort of in the middle. But for this exercise, let's focus on the left and the right rectangle. Now, the objective here is to create the rectangles under the curve in order to approximate the actual area under the curve. So the actual area under this curve down until you get to the x-axis. And so what you're going to need to do is use the sliders to change the values and then fill out the information in this table. And you're going to want to notice some patterns, and there's a natural break in the pattern here when it changes from left rectangles to right rectangles. And you want to analyze the data and then answer the questions on the next page. This is a graphic of what we're actually trying to get. This is what we ultimately want. We can't do it with this GeoGebra app, but we're going to show you how to do it later on in the lesson. So go ahead and do that. Complete these questions. Think about them critically. Should take you about 10 minutes, maybe, somewhere around there. And then after you finish that, then we'll pick up with the lesson after that. Now that you've completed the GeoGebra exercise, let's do one of these by hand so that you can get a feel for how these area under the curve problems with rectangles are supposed to go. So example number 1, estimate the area under the curve of f of x equal to x squared plus 1 over the interval from 3 to 7 using a regular partition with 8 left rectangles. All right, so there's a lot of information just packed right into that last little bit of the sentence. But the idea basically goes this way. We always consider our intervals to be A to B. And so the interval that we want here is from 3 to 7. So we're going to go from 3 to 7 like so. Then it says it wants a regular partition. A regular partition means that each subinterval is the same size. So our interval is from 3 to 7. We're going to split that up so that each of the subintervals is the same size. Well, how big should each subinterval be? Well, we know that we want to make 8 subintervals. So n is equal to 8. They're going to be 8 rectangles. And then we want to talk about this guy, delta x. And delta x is going to be equal to the size of the subintervals. Now, since all the subintervals are the same, we just need to take the length of the interval itself and divide it by the number of rectangles. Well, since the interval goes from a to b, the length of the interval is b minus a, and then we're going to divide that into n equal parts. And n is equal to 8. Sometimes they use capital N, sometimes they use lowercase n, it doesn't matter. So for this problem, delta x is equal to 7 minus 3 divided by 8, which is 4 over 8, which is 0.5. And now we can start by filling out part of the table. So the table has n rows, in this case it's 8, and we're going to list all the subintervals. So the left endpoint of the interval is 3, and the length of each subinterval is a half, so the right endpoint of the first subinterval is 3.5. Then my next subinterval starts at 3.5. We add a half to that, and we get up to 4. And we continue on in this fashion, adding a half to create all the subintervals. Notice that the right endpoint of one subinterval becomes the left endpoint of the next subinterval. So there's no overlapping and there's no gaps. We're going to cover the entire thing here. And this table is more of a guide to help us organize our data when we go ahead and draw in the rectangles here in a moment. The delta x is always a half. Next we have xi star. The I is a subscript, so that's an index. It's telling me which subinterval we're talking about. And the star indicates that it's a special point. The special point is a single point inside each subinterval that is used to determine where the rectangle's height is going to go up to. For this problem, it said that we needed to use a left rectangle. So that means each xi star is the left endpoint of each subinterval. Next we have f of xi star. So this takes the special point, the xi star, and evaluates it inside the function. The evaluation inside the function tells me how high up the rectangle goes. So this is really height of the rectangle. Now we're going to plug in each of these xi stars from this middle column into the function x squared plus 1, because that's the function we're dealing with here. It's this little parabola. And we're going to see what the heights were. Now, I also want to draw these out for you so that you can see what we're looking at. So the first one would be from the left endpoint at the 3, and it goes all the way to halfway over. Then the next one, we use the left side, and we go up to where the function hits the 3.5 marker, and then it comes down to where 4 is. And these are the left rectangles. And then I'm just going to keep drawing the left rectangles as best I can. It's actually turning out a little bit better than I thought. That one's not so good, but that's all right. I'm sure you get the idea. And there it is. There are the 8 rectangles. And now if you look at the y values at each of these, you'll see that they are the f of xi stars. Now you can't just look at the graph to figure these out. You actually have to plug them into the calculator to figure them out. But these are where those values are coming from. Lastly, we want to find the area of each of these rectangles. Well, each rectangle has a height, which is f of xi star, and a base, which is delta x. The f of xi star changes, but the f of the base, delta x, never changes. It's always a half. So here's the base, and the area is base times height. And so there we go. So 0.5 times 10 is 5. 0.5 times 13.25 is 6.625, and etc. So we get all of these values. Now that we have the area of each rectangle, the goal is to add them all up. And if you add all these up, you get 99.5. And then the logical question is, how good of an estimate is this? Hard to say at this point. But is it an underestimate or an overestimate? And we can look at the graph and where the rectangles appeared, and we can easily determine that this is an underestimate. You can see that there's this vast amount of space that never gets considered that is under the curve, and the rectangles are always under the curve. There's no place where some of them are under and some of them are over, and so I have to sort of mitigate that and figure it out. They're always under. And so this is always an underestimate. Now, a couple of questions for you to think about. What could I have changed about this problem in order to create an overestimate? And then you know that your underestimate is less than the actual area, which is less than the overestimate. And so if you wanted to come up with some bound and say, well, I think it's between these two numbers, that's one sure way of doing it. Come up with a way of always figuring out the underestimate and the overestimate, and your area has to be in between those. Now what we've been doing actually has a name. That name is a Riemann sum. It was named after Riemann, who was a German mathematician in the 19th century. And basically the way Riemann sums work is this. Let f be a continuous function defined on an interval from a to b. Partition that interval from a to b into n subintervals of equal length. The length of that interval, each subinterval, is delta x is equal to b minus a over n. Then let xi star be any number inside the subinterval x sub I minus 1 to x sub I from this partition, and then we define what the Riemann sums are. The Riemann sums are defined to be this sum here, f of x sub 1 star, so x1 star, times delta x, plus f of x sub 2 star times delta x, dot, 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 all the way up to f of xn star times delta x. Now, what are all of those little things? Well, they're all little areas. This is like area 1, this is like area 2, and they all correspond to these rectangles that we get. This is area n. So each of these a sub i's is just equal to the area of rectangle I that was formed in the same manner that we did on the previous page. Now, what's interesting here is that because we're requiring our partition to be a regular partition and the length of each subinterval to be the same number, that means delta x is always the same for each of the areas. Therefore, I can factor it out and I get just the sum of the values, that is the height. And that's your basic Riemann sum. You put it together and it gives you an estimate of the area under the curve if it's always above, and then geometrically we can talk about it being signed in a certain way. For example, suppose I had a function here that was under the curve, like so. Then we could talk about the area between the x-axis and this curve. And it's not exactly area because area should be a positive quantity. But we can sort of use what they call signed area and say, because this one is below the x-axis, it's going to have a negative area, quote unquote, on the negative part of the area. So we're using sort of signed area. That becomes important when we get to our next concept. But that's what we're doing, Riemann sums. And you found a Riemann sum in the previous problem by using the table and then adding it up. Now, what good is the Riemann sum, you might ask? Well, it's used to find the following. It's what we call the definite integral. The definite integral is the limit, known as I, of the Riemann sums of f over the interval from a to b as n goes to infinity. And the Riemann sums theorem says that this limit will exist, and we call it the definite integral of f from a to b. So what's basically happening here? We're going to let n go to infinity, and we're going to take the limit as n goes to infinity of the Riemann sums, Sn. And this is going to be equal to what we call I, and Riemann's theorem guarantees that this number exists, and it's equivalent to the area under the curve that we were trying to find in our GeoGebra example. But how does that sort of work? Well, the idea is that you have a curve and you start creating rectangles. And so like in this case right here, here's A, here's B, I have 4 rectangles. Now if I want a better approximation, I would just take more rectangles and more rectangles and more rectangles, and then suddenly the rectangles are getting extremely thin, but they are better approximating the value of the function with their height. And so as the number of rectangles goes to infinity, so this is number of rectangles, the difference between the actual area under the curve and that the area that the rectangles are producing goes to 0. And when something goes to 0 like that, we have to use a limit, and that limit exists, and so the difference becomes nothing. That makes it equal to the actual area. So that's the idea, and that's what I was hoping that you would see from the GeoGebra exercise, is that as the number of rectangles increased, the difference between the actual area and the area that's estimated by the rectangles is getting smaller and smaller to the point to where it's going to 0. Now, the limit of these Riemann sums is called the definite integral. And the notation for the definite integral is shown right here. And it looks very much like the indefinite integral that we've been studying in this class, but it has two things that are sort of extra. It's the upper limit and the lower limit. The upper limit in this problem is b, and the lower limit is a, and these are the same a's and b's that are from the interval that we are integrating over, and that we are finding the Riemann sums over and then taking the limit to produce this definite integral. We still have the variable of integration, which is x, and we still have the integrand, which is f of x. But this is what they call the definite integral, and the only difference between it and the indefinite integral is that it has these limits on it, and there's also a way to use this to evaluate the limit of the Riemann sums, which we'll see on the next page. And here it is, the fundamental theorem of calculus. And it has to do with the definite integral, and it says the following. If f is a continuous function on the interval a to b, then the definite integral from a to b of f of x dx is equal to big F of b minus big F of a, where big F is any antiderivative of little f. And that's it. That's the critical connection between antiderivatives and integration over an interval from a to b. The way you evaluate a definite integral from a to b is to find the antiderivative and then evaluate the limits inside the antiderivative and subtract. Now, it must be in this order. It must be the upper limit evaluation minus the lower limit evaluation. It must be in that order. Otherwise, you get the negative of the answer, and that's not what you want. So let's take a look and see how the answer works here. Example number 2, evaluate the definite integral from 2 to 6 of 8x minus 5 dx. So first, you find an antiderivative. So we're just going to go ahead and take the antiderivative like normal. This would be 8x squared divided by 2 minus 5x. And I put these in brackets because then the next part of this is a little extra symbol. And there's two ways to do that. I'll show you this first one with the brackets. You just go ahead and attach the 2 and the 6 to the end of the right square bracket. And that indicates that you need to evaluate in the order of evaluating this function from the top number 6 and subtracting the evaluation from the bottom number 2. Now before I do that, I'm going to go ahead and simplify. 8 over 2 is 4. So this is 4x squared minus 5x evaluated from 2 to 6. Now you may be asking, what happened to the plus c? And that's a great question. What does happen to the plus c? Well, the theorem says that you can use any antiderivative. So I'm choosing to use the antiderivative where c is equal to 0. Now what would happen if I used a different antiderivative, say one where the c had a value of 7 or something? Well, because what you do is you subtract, you're going to end up with plus 7 in the left one and minus 7 in the right one. And the 7 minus 7 is going to cancel. So the c's are going to cancel each and every time, and so we just don't include them at all at this point. So this is going to be equal to 4 times 6 squared minus 5 times 6 minus, evaluation with 2, be 4 times 2 squared minus 5 times 2. And if you work that out, you get 108. Example number 3. Evaluate the definite integral from -1 to 1 of 4t cubed minus 6t squared plus 2 dt. So first we find the antiderivative. So that's going to be t to the 4th minus 2t cubed plus 2t. And then we get evaluation from the top number. So it's going to be 1 to the 4th minus 2 times 1 cubed plus 2 times 1 minus -1 to the 4th minus 2 times -1 cubed plus 2 times -1. And if you work all that out, amazingly, it equals 0. And that's kind of weird, because what does it mean for an integral to be equal to 0? Because I thought integrals were sort of areas. Well, they're not exactly areas, right? They're signed areas. And so what that means is that this function, when graphed, has the same area above the x-axis as it does below the x-axis between -1 and 1. Now, it doesn't quite split it in half with right in the middle at 0, but it is split in half. Half of it is above 0 and the other half is below 0. You add the negative area to the positive area and it wipes it all out. Example number 4. Find the area under the curve of x squared plus 1 from x equals 3 to x equals 7. So this is the one we were doing earlier. We now know we can represent it as an integral from 3 to 7. The integrand is x squared plus 1 dx. So we'll first find the antiderivative. So that's going to be 1/3 x cubed plus x, evaluated from 3 to 7. We evaluate from the top number first. So we're going to plug in the 7. So 1/3 times 7 cubed plus 7 minus 1/3 times 3 cubed plus 3. And if you work that out, you get 328 divided by 3. And for comparison with the problem that we had done earlier, this is approximately 109.33. And our previous estimate was 99.5. So we're off by about 10%. That sort of shows you why you really want to use the definite integral over doing it with the Riemann sums. But the Riemann sums is critical to your understanding of calculus, because that's where the definite integral comes from. Let's look at some properties of the definite integral. So the first property is that the integral from a to a of f of x dx is equal to 0. Well, yeah, the integral sort of represents signed area over an interval, but if that interval only consists of one spot, there's really no area to be talked about. So that's just 0. Number 2, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Well, that's because all of this is signed, right? So it has a certain direction that it has to go. So if you talk about the integral from a to b, it's this area here. But then if you talk about the integral from b to a, it's above the x-axis, but it's going backwards along the x-axis. That creates sort of a negative situation. So you get the same value of the integral, but it's negative. So it's the same numerical number, but it's a negative value. And that's a trick that you can use if you need to flip the integration limits. If you need to flip the upper and lower limit, you just negate the integral's value. Number 3, the integral from a to b of k times f of x is equal to k times the integral from a to b of f of x dx. K is a constant. So that's just saying that we can scale it. No problem there. Number 4, the integral from a to b of f plus g is equal to the integral from a to b of f plus the integral from a to b of g, or the minus, either way. It just says that we can split integrals up over addition and subtraction. Remember that integrals are limits. They're the limits of the Riemann sums. So any of the rules that we had for limits now transfer over to definite integrals. And the last one, this is one of my favorites. It says that the integral from a to b of f of x is equal to the integral from a to c of f of x plus the integral from c to b. So essentially we have this here. So we have some function that goes from a to b, and the integral would be the area under the function from a to b. But now it says that suppose we take the integral from a to c. Well, what is that? Well, we're going to throw in a c right here. And basically this just splits it up into 1 and then a 2. So one section and a second section. And so this would be the area of the first section, and this would be the area of the second section. And it says that you can just split up the interval that you're integrating over at any point, and then take the sum of those two split parts and add them together to get the sum of the integral from a to b. Now what's interesting here is that the c doesn't technically have to be between a and b. It can actually be outside, and everything else will take care of itself. So the integral from a to b here is equal to the integral from a to c, and then plus the integral from c to b. But notice that c to b goes backwards, so it will be negative, and it will naturally subtract itself off. So it will work out. You just have to trust that it'll work out wherever the c is. Example number 5. Suppose you know the following. The integral from 1 to 5 of f is equal to 24. The integral from 3 to 5 of f is equal to 9. And the integral from 1 to 5 of g is equal to negative 6. Evaluate the following. A, the integral from 1 to 5 of f plus g. So that would be the integral from 1 to 5 of f of x dx plus the integral from 1 to 5 of g of x dx. And that's by rule number 4. And we know that the integral from 1 to 5 of f is 24. And the integral from 1 to 5 of g is negative 6. So together they equal 18. B, the integral from 2 to 2 of f of x dx. Well, since the limits are the same, the integral is 0. That's by rule number 1. C, what's the integral from 5 to 1 of f of x dx? Well, I don't know the integral from 5 to 1, but I do know the integral from 1 to 5. So in order to flip the limits around to 1 to 5, I just negate the value of the integral that I'm creating. And the integral from 1 to 5 was 24, so this is now negative 24. Example number D, what's the integral from 1 to 5 of 3g minus 2f dx? Well, we can split this up and take the constant multipliers out. So this is going to be the integral. This is going to be 3 times the integral from 1 to 5 of g of x dx minus 2 times the integral from 1 to 5 of f of x dx. The integral from 1 to 5 of g was negative 6. And the integral from 1 to 5 of f was 24. And that's equal to negative 66. Lastly, part E, find the integral from 1 to 3 of f of x dx. Well, I don't know 1 to 3, but I do know the integral from 1 to 5 of f of x dx is 24. That was given. And the integral from 3 to 5 f of x dx was equal to 9. Now I need to work out how can I produce 1 to 3. Well, 1 to 3 would be, the integral from 1 to 3 would be equal to the integral from 1 to 5 f of x dx plus the integral from 5 to 3 f of x dx. That's using that last rule where this extra c number that I'm bringing in to help me out is a 5. But this is not quite right because I don't have the integral from 5 to 3. I have the integral from 3 to 5. So I'm going to flip this over and make it negative. And then it will all work out. So the integral from 1 to 5 is 24 minus the integral from 3 to 5 was 9. And together that's equal to 15. So you had to use a couple of rules here. You had to be creative and bring in that extra 5 because that's the information that sort of connected 1 and 3. Lastly, we can do definite integration with substitution. Let me show you how. There's a typo here. This x should not be there. Take that x out. All right. So the problem is evaluate the integral from 1 to 9 of the square root of 2x plus 7 dx. So I want to let u be equal to 2x plus 7. And du is equal to 2 dx. And dx is equal to du over 2. And now we substitute. So I'm going to do the indefinite integral first. And so let me write it out. So it's the integral of the square root of 2x plus 7 dx. That is going to equal the integral of the square root of u times du over 2, which is equal to 1/2, bringing the 2 out to the front, the integral of u to the 1/2 du. And now we integrate. So we're going to take the 1/2. We're going to raise the power by 1. That's going to create a 3/2 in the exponent. And then we divide by 3/2. I'm going to multiply by the reciprocal. And I'm going to bring the original u back in as 2x plus 7 to the 3/2 plus 2. The 2's cancel. And that leaves me with an indefinite integral of 1/3 times 2x plus 7 raised to the 3/2 power plus c. Now we want to do the definite integral part of this. So we can choose c to be 0 and just wipe it out. And then we evaluate this from 1 to 9. So the definite integral part would be 1/3 times 2x plus 7 raised to the 3/2 evaluated from 1 to 9. 1/3 is a multiplier times the whole thing. So in actuality, it can come out to the very front of everything. And then we're going to have 2 times 9 plus 7 raised to the 3/2 power minus 2 times 1 plus 7 raised to the 3/2 power. And if you work all that out, you get 98 over 3. Next time, we'll be looking at applications of the definite integral, including something called the Gini index, and finding more areas of shapes using the definite integral. Thanks for watching. We'll see you next time.